Say, oh yeah, I kind of got to go, but hey, your life doesn't mean anything. So one of those two. Yeah.
7 hours, but it's $70 doesn't take me. So I get one.
You can need my homework sheet back. I guess it's kind of popular today.
What's that?
Do you need this back?
No. I don't think so. I think last time we ended up doing a couple of the problems where we did the algebra of combinations and permutations, or at least permutations, I'm sorry. So I think we have to do several that involve the combinations. Talk a little bit about Pascal's triangle, talk a little bit about the binomial theorem as well. Okay? So hopefully today we're going to finish up that thing for the examination. That's going to be next Wednesday. But if not, we'll finish up on Monday, and then we'll spend the rest of the time reviewing. Okay. So guys, any questions as to what's going on before we get started? Okay. So let's start off with a pretty basic property of being able to prove the algebra of a combination. Okay. So we have this fairly simplistic one. We have n minus 1, n minus 3. And we're claiming that that's equal to n minus 1 div 2. Okay. So basically, guys, if I have, let's say something like 5 combination 3, I just multiply 5 times 4 and then divide it by 2. Okay, if I wanted to do that combination without having to go through and do the basic definition. Right. Just a reminder, the formula for the combination NR, okay, just in case you guys might have forgotten, n factorial divided by r factorial n minus r factorial. So all we're going to be doing is we're just going to be substituting n minus 1 and n minus 3 back in for n and r respectively in this.
Why are you choosing combination on this? Because you did not mention on this one, the other two you mentioned the p.
Right. When it's written like this is just the way combination's written.
Okay.
You don't have to put a c in front of it. It just has to have the parentheses.
And for permutation there will be a p.
Correct.
Okay.
Okay. Right. So just to substitute this back into our formula, okay, this would be n minus 1 quantity fact divided by r fact, which is n minus 3 fact. And then we're going to multiply that by n minus r quantity fact. So I'm going to use a bracket, and I'm going to say n minus 1 minus n minus 3, and then put the factorial on the outside there. Okay, so I'm just using the different levels of the brackets just because I know we're going to have a binomial, so I want to make sure I put that in parentheses.
Can I have one of those worksheets, please?
Sure. All right. I'm hoping that everybody sees that the next most obvious thing to do is probably just simplify inside of the brackets.
Which one is the r over here?
What's that?
Which one is the r?
So the second one is always r,
And
the first one's always n.
Okay.
Okay. So whenever we substitute the top in for n, the bottom in for r. Okay. So does that make sense to everybody, guys? Any questions? Okay. We probably want to simplify inside the brackets, which actually works out fairly nicely. If we simplify inside the brackets, what are we left with there? 2, right? Because we have n minus n, they cancel out. And then we have negative 1 minus a minus 3, so that just works out to be 2. So we wind up with n minus 1 fact divided by n minus 3 fact divided by 2 fact. Okay, I'll keep the 2 inside the bracket so that when you guys go home, you remember where that 2 came from. Okay, does that make sense to everybody? Everybody okay with the algebra of simplifying inside the brackets? Now we need to try to make it look like n minus 1. Notice it's not a combination. So we looked at someone like this last time, so this might be one where we can expand and cancel instead of trying to get the common denominator, because we don't have to make it look like a combination formula. So if I would expand n minus 1 fact, that would be n minus 1 n minus 2, n minus 3, all the way down to 3, 2, 1. And then in the numerator, or I'm sorry, in the denominator, this would be n minus 3, n minus 4, all the way down to 3, 2, 1. Okay? Now we still have that 2 factorial. So in brackets, let's see. So, and then times, I'm going to put the expanded form of that, the 2 times 1, in the brackets. So, everyone okay with that, guys? Any questions about what we did to expand those? We just used the definition of factorial to just write down in descending order of the integers. Okay? I'm hoping everybody can see that all we're going to do at this point is cancel out some of the common factors, okay, just like we always do. Okay? So it looks like everything from n minus 3 down to 1, and everything from n minus 3 down to 1 are going to cancel. So it looks like that I'm going to end up with n minus 1, n minus 2, and then in the denominator we get 2 times 1. So, is that okay with everybody, guys? Just going through, simplifying, doing the canceling. Okay, hopefully not too difficult with that. All right. To make it possibly look like n minus 1, we might want to FOIL it out and then collect like terms, but I think if we FOIL it out, we're not going to get anywhere close to this. So I think this is one where we actually disprove it, okay, just by going through and doing the algebra. So clearly, this can't be equal to n minus 1 over 2. Okay. There's probably an easier way to be able to figure this out. So what would have been easier for us to do rather than go through and do the algebraic proof? So, yeah, just try plugging in a few numbers, right? And seeing if it works, okay? We just always assume that it's going to work, okay? But this one didn't work out. So another way we could have done it is just a counter example, okay? So, but we could always do the algebraic proof, and the algebraic proof works out okay. All right. So guys, any questions about what we did to be able to disprove this? It says to verify it or to disprove it, I guess, and this one we unfortunately had to disprove. So no questions, guys? Okay. We could do the same thing with the next one, okay? This one's got several different variables in there, so it might be a little bit more algebraically taxing, but hopefully not too terrible, okay? So, again, this top part's going to be the n, and the bottom part's going to be the r for us to substitute back into the formula. So we have n minus r minus 1, and then n minus r minus 3 as a combination. We're just going to go ahead and substitute that back into the combination formula, and then we're just going to whack it with the algebra stick. Okay, so if I want to substitute, maybe somebody could help me to set this up with the substitution. So can anybody tell me what this might look like before we do any sort of algebra to it, just the setup for it?
So the top one will be n minus r minus 1, right?
Okay. So n minus r minus 1.
And the bottom one will be n minus r minus...
Factorial.
Oh, factorial, sorry.
Right, yeah, that's important. Okay, and then go on.
The bottom one will be n minus r minus 3 factorial.
Good.
Then n minus r minus 1. You may want to put that in a bracket actually.
Okay.
Okay. Minus n plus r plus 1.
Okay. Or do you mind if I write it like this? N minus r minus 3. 3. And then just put those in parentheses. So that way when people go home, they're like, well, where did the plus signs come from? Okay, so that way they understand that it was a distribution process. Okay? So, yeah, we probably want to have that factorial after the bracket as well. Okay. All right, so does that make sense, guys? Any questions about the setup for this? Okay, all we're doing is we're just immediately substituting back into this formula. Okay, so it's not that big of a deal. It's just a substitution, just like you guys did in Algebra 1, except there's a lot more stuff going on. Okay. So, the next thing we might want to do is we might want to clean up what's inside the parentheses here, okay? Or inside the brackets, all right? And can somebody tell me if they were to clean up inside the bracket what we'd end up with? Yeah, probably 2, right? Because we have an n minus n, we have a negative r minus a negative r, and then we have negative 1 minus a negative 3. So once again, it just works out to be 2. It kind of makes sense because the difference between these two values is 2, no matter what the values of n and r are. okay? So, this is going to work out to be n minus r minus 1 fact, n minus r minus 3 fact, and then in brackets I'll put the 2 fact. So that's nice and easy, right guys? A lot better to look at than the first one that we had. Suggestions at this point as to perhaps how to simplify. And let me ask you guys this question. Should we try to eliminate some things, like by writing out the factors like we did here, or should we try to get a common denominator? What do you guys think? Done?
I think you can try to do that because
Done. Sorry,
I
yes.
think click to the point when you can foil, because in the on the right hand side it's foiled out.
Yeah, I mean, it doesn't look like a combination on the right-hand side, right? So to me, if it doesn't look like a combination or permutation, there's no reason to get a common denominator. I think we should just expand it, and then hopefully some stuff will cancel out, okay? I like what you suggested, okay? So I'll say it again. If you don't have a combination or a permutation on the right-hand side, just go ahead and try to cancel stuff out. If you do have a combination or permutation that you're trying to prove it equal to, that's when you need your common denominator. Okay? So let's expand this. The numerator. If I were to expand that, okay, that would be n minus r minus 1. What would be the next factor down from n minus r minus 1?
minus 2.
Yeah, n minus r minus 2, right? Okay, n's and r's are constant, they're not changing. And then n minus r minus 3, right guys?
Can't you just write the n minus r minus 3 factorial
Sure.
instead of all?
If you want to, that's perfectly fine, but if, in case people aren't able to see that, I want to make sure that they understand how to write everything out, okay? And then in the denominator, we can expand n minus r minus 3 and 2 factorial. So that'll be n minus r minus 3, n minus r minus 4, all the way down to 3, 2, 1. And then we can't forget that there's the 2 factorial as a result of the n minus r quantity fact. So I'm going to bracket this and say 2 times 1. Alright, hopefully it's obvious that everything's going to cancel from the numerator and denominator except for the n minus r minus 1, n minus r minus 2 factors, and then also the 2 times 1 that we have left over. So, what we're left with, okay, I'll write this up here, is n minus r minus 1, n minus r minus 2, divided by 2 times 1, which is 2. So, let me let you guys check that out, make sure that's okay. Any questions so far, guys? Just expanding and then just simplifying stuff, okay? Just like what we did earlier in the course when we did this stuff with sequences in series. Alright, John, go ahead, sir.
Yeah, I don't for C, why, you're saying that doesn't equal n times n minus 1 over 2, so how is that the answer?
Because remember, the objective is to prove that one side equals the other, right? These two are not the same, because if I were to FOIL this out, that would be n squared minus 3n plus 2 over 2. This would be n squared minus n over 2. Clearly, these two are not equal to one another. So what we've actually done is we've disproved it.
Oh, we can disprove. Wait.
Oh, yeah.
So we can prove or disprove.
Correct.
So,
Yeah. It's either verify or just show it doesn't work. Okay?
oh, okay.
So it could be possible that it doesn't work, just like any sort of proof. You could use a counterexample to show that anything doesn't work. Well, what would have probably been easier is if we just plugged in 5 right here, and plugged in 5 on the right-hand side. But that would have assumed that we knew it didn't work at the beginning. Okay? So does that make sense, sir?
Yeah, so basically the original statement is false, is that?
Right. And we just went through and verified that it was false. Okay?
Yeah.
All right. So, back to what we were doing with letter D. Any suggestions as to perhaps how to
Foil it?
proceed? Yeah, probably FOIL it out. And unfortunately, it's one of those where we're going to have 9 terms, I believe, when we FOIL it. Okay, so it's not a big deal. Okay, just a big FOIL problem. Just in case you guys forgot, what you do is you take the n, distribute to all 3, take the negative r, distribute to all 3, take the negative 1, distribute to all 3. Okay, so it's just like a FOIL problem, except instead of having 4 terms, you're going to have 9 terms. Okay, so let's just go ahead and do that. So n times n, n squared, n times negative r, negative nr, n times negative 2, negative 2n. Now I'm going to multiply by negative r times n, negative nr. Negative r times negative r is positive r squared, negative r times negative 2, positive 2r. Negative 1 now, negative 1 times n, negative 1 times negative r, positive r, negative 1 times negative 2, positive 2, all divided by 2. Okay? All right, so does everybody see how that FOIL works for that? All we did was we just took the first term, distributed to all three, the second term distributed to all three, third term distributed to all three. Okay? So just like a FOIL problem, just a little bit bigger than what you guys are used to. Okay? Suggestions at this point, now that we FOILed everything out?
Like terms?
Yeah, there's some like terms in there. Okay? In fact, I believe there might be 2 pair of like terms. It looks like that there's an NR and an NR here.
Then 2n.
Yep, there's a 2n and a negative n.
2n.
So 2n and a negative n. And then I think we have a 2r and a positive r.
Yep.
So 2r and plus r. So it looks like we actually have 3 pair of like terms in there. Okay, so let's combine those, and then I think we can do the last step fairly easy after that. Okay? So by combination of like terms, n squared, negative r and negative nr is going to be negative 2nr. Negative 2n and negative n is negative 3n. And then 2r and r is positive 3r. And then we're just going to bring down the r squared and the 2. So plus r squared plus 2 divided by 2. So just some basic combining of like terms, nothing too difficult with that. We're trying to show that it equals n squared minus 2nr minus 3n plus 3r plus r squared, and then plus 1 off to the side. I think everybody can clearly see that since we're dividing by a monomial, we can split that off and then just divide the 2's to get the 1 out of that. So, what's that?
Are we, like, if we just left it like on the test, is that fine? Like,
Since it says to verify that it does equal
okay.
this
I
right
didn't see
here,
that, okay.
right, so we would have to break that off, okay? It, unfortunately, it doesn't just say simplify, it says to verify that it equals the other side, okay? So, if it just said to simplify, then yeah, that'd be fine to do that. But r squared 2 plus 1. Okay. So guys, there was a fairly elementary example and then an intermediate level example of how we go through and try to work with our combinations. Okay, so any questions I can answer for you all about how we're going to work with these combinations? Okay, just basically just big algebra problems. Okay, these two aren't too bad because you don't have to make it look like a combination. Now, unfortunately, the last one that we're going to look at, this is one to where it's going to be more difficult because we have to make 2 combinations somehow look like another combination. Okay? In fact, this is actually a proof of, by the way, if we verify this does work, this is actually proof of Pascal's triangle. And I know some of you guys have been talking about Pascal's triangle, some of you guys have no idea what it is. So I want to show you guys, first of all, what Pascal's triangle is and how it's derived. Some of you guys might know, some of you guys might not know. Okay? And then I'll show you guys why it might be useful. Okay? So, and you don't have to write this down if you don't want to. But I'm just trying to show you guys an application of why you would ever want to prove a permutation or a combination theorem. Pascal's triangle, you start with a 1 at the top, and then you just drop 2 more 1's down. Okay? And then what you do is you just add the numbers that are in succession to get another number out of it, and then you put 1's on the outside. Okay? So there's 1's that go all the way down diagonally, and then to get the number in the middle of that, or the numbers, you just add the 2 adjacent numbers to one another. Okay? So for instance, the next row would be 1, and then 1 plus 2 is 3, 2 plus 1 is 3, and then you put a 1 on the outside. Okay? If I wanted to get the next row, that would be 1. What would be the next 3 numbers by Pascal's triangle?
4.
4, 6, 4, right? 4, 6, 4, and then 1. Okay? If I was to do one more row, just to say that we did, that would be 1,
5, 10,
10,
5.
5. Okay. So you guys might be thinking, okay, well that's great, and that's a pretty neat trick, but you're like, okay, well where would I ever use that sort of thing? Okay? I want you guys to go into your calculator, and I'd like for you guys to evaluate 5 combination 3 in your calculator. Okay, by the way, I've already done it.
10.
Yeah. 10? Okay, I already knew that. You ready? I went down to the 5th row, so this is row 0, 1, 2, 3, 4, 5th row. And then I went over to the 3rd element, 0, 1, 2, 3. Hey look, there's a 10. There you go. You can evaluate any combination that way, okay? Go ahead in your calculator, evaluate 4 combination 2 in your calculator. I've already got it done. 6, right? Because you go to the 4th row, you go to the 0, 1, 2 element, right here. So right here, this is 4 combination 2. You always start with a 0th element, okay, because like a 0th power, okay? So 4, 2 is 6, 5, 3 is 10, okay? You can use Pascal's triangle to evaluate any combination, okay, anytime you want it. Like for example, let's say you didn't have a calculator and you wanted to do like 7 combination 4. Okay, we did that the other day and I think we got something like maybe 35 out of it. Eventually you would get the same thing. Okay? Somebody else do me another favor. Somebody go through and expand a plus b to the 5th. Okay, just sit there and do it. I've already got it done, by the way.
A to the power 5th plus 5ab 4 plus 10ab cubed plus 10ab squared plus 5b plus
A
1.
fourth b.
Should be-
Yeah. Guys, these are the coefficients of the expanded binomial a plus b. Okay, if you don't believe me, of course you'll believe Mathematica. Everybody believes Mathematica because, you know, it shows everything. Let me bring it up just to show you guys that it does work. By the way, I'm just showing you guys like why you would ever care about this thing and what the uses are for it. If we would ever bring it up. It might take like 15 years because it's a huge program. I thought I told it to boot up. Well, if it doesn't boot up, that's fine.
Or go to Wolfram.
Yeah, I'll go to one or Alpha or Wolfram Alpha online. So, everybody's favorite friend, right? When you can't figure out something in Calc 2, where do you go? Wolfram Alpha. So let's just say I wanted to expand x plus y to the 5th. Okay, you can type it in Wolfram Alpha. And then it'll give it to you right here. I want you guys to check out the coefficients of this. 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. So let's say for some reason I wanted you guys to expand a plus b to the 6th, okay? How many of you guys want to sit there and just multiply that out 6 binomials? You do, Donnie? Let me know how that works for you, okay? Or we could just do 1, 6, 15, 20, 15, 6, and 1, right? We get to the next row. In fact, let me verify that these are indeed the coefficients that would do that, or that would give us to the answer. Okay? I don't want to do pro. I don't want to go with pro. All right. So there we have the coefficients. 1, 6, 15, 20, 15, 6, and 1. It's almost like Mathematica really isn't that smart, and your TI 87 or 89 calculators aren't that smart.
Are you a wizard?
No, I'm not. Oh, you mean I actually wrote the program, and I just made all this stuff up, Chris. Like, I'm actually just getting you guys to believe this stuff like this. So, no, I don't work for the government.
It's
so,
a conspiracy.
It's definitely a conspiracy. That's completely what I'm doing. No, I mean, that's what Pascal's triangle does, and it does a lot more stuff than that, okay? So there's actually a Fibonacci sequence that's embedded within there. There's so many things that are cool about the Pascal's triangle. So like for instance, like you guys, and when I do the combinations in my head, like you know, I'm sitting here and I do the combinations. How are you guys thinking? How does he do that in his head? I really just know Pascal's triangle. That's all I'm doing. I'm not really doing anything smart. So yeah, I'm not really as smart as you guys think I am. Although many of you guys probably didn't think I was smart anyway. So anyway, this is Pascal's triangle, okay? So if you guys are on your test and you forget your calculator, just go ahead and use that, okay? It's just as easy. All right. Now the question, our purpose is, and how many of you guys have ever seen this before, like in pre-calc? Okay, so some of you guys already know about this, okay? How many of you guys ever proved it? Yeah. You did? Did you really?
I think when I did differential equations, we did something like that.
Really? Oh, you actually proved it?
I think we did something.
Yeah,
like
you
that.
probably can in differentials because you do the you do a little bit with the series stuff. So it is possible. You might have done it then. Okay. Maybe you worked with the binomial series and you might have proved it inadvertently there. So.
But I don't remember it.
No, that's okay.
You know what I'm saying?
Oh yeah, that's okay.
I don't remember the steps now.
No, that's okay. But I mean, just the fact that you've been exposed to it's a good thing. Okay. So what I want to do, guys, is I want to prove Pascal's triangle. In other words, how do I know that if I add up these two combinations, I get this combination, right? I mean, that's literally what we're trying to prove, okay? So let's say for some reason that, I don't know, this is element NR, okay? And you guys, like I said, you guys don't have to write this down. Let's say this is element NR plus 1, okay? So that's just the next element over, okay? Then 15, wouldn't that be n plus 1 r plus 1 by the formula, right guys? Because that's the next row down, okay, and it's the second element over. So basically what we're saying is that n combination r plus n combination r plus 1 should be equal to this, okay? That's what Pascal's triangle says, and that's Pascal's theorem. Our job is to be able to prove that, and that's what we're going to do using all the stuff that we know so far. So let's go ahead and prove that, okay? So here's our formula, it's right here. I just use the indexes n minus 1 instead of plus 1, etc. So I could have said like the previous n, or I'm sorry, the previous r and the next r is equal to n combination r. I think I made the formula actually a little bit easier for you guys doing it this way. All right, so let's go over here and do this. Okay, we'll probably need both boards to be able to do it, but this is our proof of Pascal's triangle. All right, so I want to say that n minus 1 combination r minus 1 plus n minus 1 combination r is equal to n combination r. All right. This is actually fairly similar to the problem we looked at on Monday, where if we have a difficult side and we have an easy side, we want to tackle the difficult side and make it look like the easier side. And we don't want to do the opposite, because then we have to get into partial fraction decomposition. We don't want to deal with that stuff. So let's just use the definition of combination on both of the left-hand side combinations. Okay? So this would become n minus 1 fact, r minus 1 fact, bracket n minus 1 quantity minus r minus 1 quantity fact. Okay, so that's the first of the two. Okay. For the second one, I'm going to use the exact same definition, except wherever I see an r minus 1, I'm just going to plug it in r. So n minus 1 fact, r fact, and then n minus 1 minus r fact. Okay, that's supposed to be equal to n combination r, hopefully, after we beat it up with the algebra stick for a little while. All right, so any suggestions as to perhaps how we could even attempt to make our left-hand side look like our right-hand side? What's a good place to start, besides going home? Yeah, simplify the bracket, right guys? I mean, isn't that the process we've been using all day? If it worked the first two times, let's see if it'll work this time. What's that? We're not insane, definitely not. That's the definition of insanity, right? Like doing the same thing over and over again and expecting to get the same or different results. All right. If I was to simplify what's inside the brackets, we have n minus 1 minus r minus 1. So what do the brackets simplify into? It's not 2 this time.
It's n minus r.
N minus r, nice gentleman. Okay? The 1's cancel out, or actually the negative 1's cancel out, and we're left with n minus r fact. Okay. For the second fraction, I don't believe that we can simplify anything, can we, guys? Okay, there's no like terms, so we're stuck with what it is. So that's just going to be plus n minus 1 fact, r fact, and then I'll just use parentheses just to keep it consistent. And I'm going to switch around the order of what's inside the brackets. I'm going to say n minus r minus 1, just to make it look as close as I can each time. Okay? So in other words, I just wanted to make this binomial look like this trinomial as much as I possibly could. Okay? All right, clearly that's got to be equal to something, so it's equal to n combination r. All right. So since we're trying to make left-hand side look like right-hand side, okay, and the right-hand side is not a polynomial or a fraction, okay, it's going to be a combination. This is where we can't go through and expand and cancel out, okay, as much as we'd like to, we can't. So what's the other process that we have to utilize? Yeah, we'd have to get a common denominator for this. And for some of you guys, being able to get the common denominator might be difficult. So what I always like to do is I like to write out whatever I think might be the pairs that might get me to a common denominator. So let's write out r minus 1, and you don't have to write this out, by the way. This is just to kind of help some of you guys see the common denominator. So I know that these two look very close to one another. Okay, so this is r minus 1, r minus 2, all the way down to 3, 2, 1. This is r minus 1, r minus 2, 3, 2, 1. Okay? If I'm just looking at those two factors, what is the common, or what is the least common multiple or least common denominator between these two expressions?
R.
R factorial, right? Guys, isn't it so plainly obvious, now that I've written out, that r minus 1 factorial has everything that r factorial has except for r? Can everybody see that? This has everything that r factorial does except for r. So basically, all I would have to do is multiply both sides by r, and that would give me the r factorial for this. Okay? So does everybody see that if I was to do this, that these two would be exactly equal? Does that make sense to everybody, guys? Okay. This might be helpful when you guys are doing your homework problems. Okay? So the LCD between these two is going to be r fact. What about between n minus r fact and n minus r minus 1 fact? Well, n minus r fact is n minus r, n minus r minus 1, n minus r minus 2, all the way to 3, 2, 1. And then n minus r minus 1 fact is n minus r minus 1, n minus r minus 2, 3, 2, 1. Okay? What would be the least common multiple, or least common denominator, if you would, between these two expressions? N minus r fact, right? Guys, isn't it plainly obvious that n minus r minus 1 has every single factor as n minus r fact except for n minus r? So what I would do is I would multiply both sides by n minus r to get those equivalent, okay? That's going to help you guys to be able to see what you need to multiply by one to get to the other to maintain equivalent fractions, okay? So, does that make sense to everybody, guys? It's just like in algebra. Your teacher hopefully showed you how many x's or how many factors you need to get to the other
But
fraction.
why are you saying that we are multiplied by n minus r fact? We are multiplied by just n minus r.
Right, because if you multiply that, that gives you
He said
the factorial. You're just missing one factor. You're not missing all the factors.
Factorial, okay.
You're just missing one factor to go from this n minus r minus 1 fact to n minus r fact. And that factor just happens to be n minus r. Okay? So just line them up, see what you're missing, and that'll help you guys to be able to figure out what the common denominator is. Okay? So I think, and you guys might be able to correct me if I'm wrong, but the least common denominator is going to be r factorial, n minus r factorial. You always pick the one that has everything in it, right guys? Like if you had a choice between x cubed and x, you pick x cubed because it has all the x's, okay?
Did you write LCD just because you didn't want to write the whole thing out, or was that?
Oh no, what we're going to do is the next step, we're going to rewrite the fractions with the LCD.
Oh, okay.
I'm just
I
saying
thought,
that-
I thought you were like combining.
No, sir. No. This is just what is the least common denominator between all of this mess right here. So that way when you guys go home, you're like, oh yeah, that's the LCD, okay?
Okay.
And above is how I got to the LCD. Okay, does that make
Okay.
sense, Andre?
Yeah, yeah.
Okay. Let me do that on the other board just to make sure we have enough space to be able to work with this. So I'm going to rewrite each of the fractions now with r fact n minus r fact, because that is the common denominator. I'm going to carry over the original numerators from what we had. So we already had an n minus 1 fact, and then we had an n minus 1 again, I believe. N minus 1 fact. Now we have to play that game of what did we multiply by one fraction to get to the next fraction, okay? The good news is, guys, it's already done. Because if you look over there and you look what I wrote in blue, that is exactly what you would have to multiply by. It's almost like I did that to make it so painfully clear that somebody's hitting you in the face with it, okay? Does everybody see that to go from r minus 1 fact to r fact, I would have to multiply by r factorial. That's exactly why I wrote it out.
Multiplying by r, not r.
I'm sorry, r, you're correct, okay? Sorry, I was saying to get to r factorial. Sorry about that. So I'm going to multiply the top by r, okay? Because that's what I'm missing. We had r minus 1 fact. We need to get to r fact. So to get there, you multiply by a single r, okay? What about in the other expression? If I was to ask you guys to be able to multiply by something, okay? What am I going to multiply by to get to n minus r fact?
N minus r.
N minus r, right guys? And if you don't believe me, look right here. It's basically just slapping you in the face as telling you, what do you need to multiply n minus r minus 1 by to get to this, okay? Like I said, guys, when you go home, write it out, okay? It'll literally take you a minute to write it out, and then you guys will see what you need to multiply by, okay? Okay. Is this clear, guys? Any questions so far? Now we have equivalent fractions. This is supposed to be equal to n a combination r, okay? It looks like it's going to get there. Okay. Any suggestions now that we have a common denominator?
Add them. No, hold on a second.
Well, I mean, what's the whole purpose of getting a
No,
common
take n
denominator?
minus 1 common. N minus 1.
Yeah, let's make it into one fraction.
Okay.
Okay, I like that. I mean, the whole purpose of getting like fractions is to be able to get to a single fraction. So, I mean, at least let's do that. Yeah. And we knew this, right guys? I mean, that was the basic process for mathematical induction. You get a common denominator to add the fractions together, right? So we would write this as n minus 1 fact in the numerator times r plus n minus 1 fact times n minus r. Right, guys. Any suggestions as to perhaps now what we could do in the numerator?
N minus 1 common, right? Fact.
Yeah, isn't there a common factor of n minus 1 factorial? Okay, I mean, I would factor that out if it's a common factor. You guys can plainly see that these two are common factors. So all I'm going to do is I'm going to factor that binomial factorial out. Okay, so this is going to be n minus 1 fact. Once I factor out that factorial, don't I just have 3 terms that are left over? What are the 3 terms?
R plus n minus r.
R, n, negative r. Good. So we just have r, n minus r plus n minus r. Now that's not a factorial. That just is what it is. R fact, n minus r fact. Okay, that's supposed to be equal to n combination r. Next step, almost plain as day. Guys, what's the next thing we would do?
Cancel the black
Yeah.
term.
There's a positive R and a negative R. That's just the inverse addition property, or just equal to 0. Okay. So those go away. We are now left with n minus 1 fact times n divided by r fact, n minus r fact. Everybody okay with that, guys? Any questions about what we did to get to this point? Okay, all the algebra, we're just factoring, canceling, nothing too difficult. All right, any suggestions as to where to go now? So, Joe?
Make it n factorial on the top.
Yeah, because you have everything less than n, right? You have n minus 1, n minus 2, n minus 3, all the way down to 3, 2, 1. Well, now you're multiplying by n. So this would basically be like if I had 5 fact times 6 is actually equal to 6 fact, okay? It's the same idea. You have one less factorial and the next factor up. So this is n factorial, r fact, n minus r fact. Okay, that looks good. Yeah, that's it. Because that's the very definition of a combination, right?
Hold on, can you explain again how I get that it's how you have it's 1 less 5 factorial times 6, so why does it just become n factorial? Why do we get rid of
Okay.
the n?
If I had,
Because wouldn't that be changing the value?
no, if I have 5 fact times 6, that's 5 times 4 times 3 times 2 times 1 times 6.
Yeah, that makes
And then equals, and then you can put.
So if I had n minus 1 fact times n, that's equal to n minus 1, n minus 2, n minus 3, 3, 2, 1 times n. Or,
That's just by definition.
yeah, that's the very definition of what a factorial is.
Okay.
I can move that n in front, and I get n factorial out of that. Okay? Does that make sense, Andre?
Yeah.
Okay. Yeah, maybe if you write it out and you see it, sometimes it's more helpful than just trying to sit there and try to like just assimilate it sometimes. Okay? All right. So guys, we've just proven Pascal's triangle. Okay. Now that's this one's a fairly simplistic proof. Okay, when it comes to like doing combination and permutation proofs. For those of you guys that are going a little bit higher in mathematics, you'll have to do this with integration. You'll actually have like binomial integrals and series and things like that. So it'll be much more difficult than this, okay? This on a scale of like 1 to 10 in terms of difficulty in the grand scheme of like what you would do with this, probably like a 1.5, okay? So all the stuff that we've done before this is like a 1, maybe even a half so far. So we haven't even introduced calculus or series into these. So that's when it starts getting really tough, okay? But for right now, we're just doing the elementary stuff, okay? All right, although I'm not saying it's easy, okay? There's a difference between elementary and easy, right, guys? Because, I mean, obviously, this is very difficult, but in the grand scheme of the scale, it's elementary level.
That's on real analysis, not on discrete math, the one you're talking about.
Oh, yeah, right. But I'm just saying, like, later, like, in your mathematical careers, I mean, this could be much more difficult, okay? In fact, for any of you guys ever worked with the binomial series, okay, it's a very difficult series to work with and try to do anything with. So, anyhow, all right, guys. Any questions I can answer about the proofs involving algebra of combinations and permutations? Okay, I think this is the first half of assignment 10, which is due after the examination. Although I would strongly suggest you guys work through that to prepare for the examination. As I noted on the last examination, some of you guys did really well until you got to induction, and that's just because the whole assignment 7 was induction, and guess what, some of you guys didn't work before the exam, induction. So instead of getting like an 80 or a 90, you got a 50 or a 60 or a 70 because you lost like 30 points. So you guys don't want to do that, right? Okay, so make sure you guys practice it, work on it. If you need help, come and see me for what I can do. Okay. All right, guys. So now that we know how to try to work with the binomials or some of these things with the combinations, the last topic we're
But
going to
we didn't prove it.
What's that?
We didn't prove this.
Yeah, we did.
This is n factorial.
That's it.
Yeah.
Oh yeah, okay.
Yeah, that's exactly it.
Okay.
Okay. Yeah, we proved it. I wouldn't lie to you. Not on purpose.
Okay.
Okay. That's all right.
I forgot that. Yeah.
That's okay. Yeah, that's the very definition of combination. So we're done. Okay. So guys, we looked at Pascal's triangle. We saw one of the applications was expanding a binomial. Okay. In fact, I plugged it into Wolfram Alpha and I showed you that you can expand a binomial using the idea of a binomial theorem. And that's exactly what we're going to do. So this is our binomial theorem. It's actually a binomial series. Now we're not going to prove the binomial series. Proving a binomial series is much more difficult than being able to prove just the combinations that lead up to it, okay? So what we did just now is like maybe about a quarter of being able to prove this guy. Okay, we're not going to prove it, we're just going to assume it's true. So if I want to expand any sort of binomial to the nth power, I have a series k equals 0 to n, and what I do is I just keep decreasing the power of the first term and increasing the power of the last term by 1, or the last factor by 1, and then multiply by a combination. Okay? This is exactly the formula that when I plugged that into Wolfram Alpha about 20 minutes ago, that's how Wolfram Alpha does this sort of thing. So if you're a computer programmer, okay, and your boss asks you to write a program that's able to expand a binomial, this is what you guys would have to do with it. And the computer just recognizes the syntax, does the spacing, and does the printing based upon that. Okay? I remember in one of my last computer science classes, I actually had to write a program that output a binomial theorem. A student put in, I guess it was the nth power, we had a fixed binomial. He made it really easy for us. So, but it could be a much more difficult problem if we had to actually input the variables. So, anyway, I just want to show you guys an example of how to go ahead and expand something using the binomial theorem. Okay, so if I had 2a plus 5b to the third, okay, that's probably a problem that you guys could just do without the binomial theorem, and it would probably be just as efficient to do it with that. But I just want to show you guys what it would look like if we did. Okay, so I'm going to use the binomial theorem, and I'm going to expand that binomial. Okay, not meant to be difficult. Okay, so 2a plus 5b cubed. Let me bring up the binomial theorem again too, because I want to make sure we have that. In this example, a is really equal to 2a. Okay, so a equals 2a. Okay, so that's like the placeholder for that. B is equal to 5b. And then n is going to be equal to 3. That's our exponent. So essentially, if I wanted to go through, use the binomial theorem to expand, okay, this would be equal to series k equals 0 to 3, okay, because that's our n right here, 3 combination k, quantity 2a to the 3 minus k, and then quantity 5b to the kth power. Okay, so all we did there, guys, was we just subbed in the values back into the binomial theorem. That's it. Okay, it's not meant to be difficult. It's just a straight substitution up to this point. So does that make sense to everybody, guys, as to how we substituted? We identify a and b, we identify n, we substitute. Now it's just a series problem. Okay, and we know how to work with series. We just go ahead, we keep increasing k by 1 each time. Okay, so we're going to start with 0. So the first term in this expanded binomial is going to be 3, 0, 2a to the 3 minus 0, and then 5b to the 0. Okay, so everybody sees that, guys? All I did was I just substituted k equals 0 back into our binomial theorem. To get the next term, I increased the index by 1. So now this is going to be 3 combination 1, 2a to the 3 minus 1, and then 5b to the first. For the next term, I'm going to increase k by 1 again. So this is going to become 3 combination 2, 2a to the 3 minus 2, 5b squared. And then finally we get to the third term, which is our upper bound of our series. So that's going to be 3, 3, 2a to the 3 minus 3, and then 5b. So let me give you guys a moment to copy that down. All we're doing each time is we're just increasing k by 1. That's it. Okay, so we just start by defining what A, B, and N are. We plug it back into our series, and then we just expand that series. Okay, so any questions so far about what we've done, guys? Just basic plug and shove. Okay, nothing too difficult. Okay, now we're going to compute. Okay, so we can either use our calculators, or we can just go ahead and use general knowledge. Okay, we could even use Pascal's triangle, right, guys? We know that 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So guys, aren't these going to be the combinations to evaluate 3, 0, 3, 1, 3, 2, and 3, 3? All right, so we don't even need our calculators, I don't think, for this. Okay? We know that 3, 0 is 1. 2a to the third is going to become what, guys?
8a cubed.
8a cubed. And then 5b to the 0 becomes
1.
1. Right, guys? So that's the first term. Okay? Does that make sense to everybody, guys? Just basic evaluation. For the second term, we know what 3 combination 1 is. 3 combination 1 is 3. 2a quantity squared now is going to be 4a squared. And then 5b to the first, that's just going to be 5b. Okay, so that's our second term. We're going to clean this up in a minute. Okay. For our third term, we already know what 3, 2 is. 3 combination 2 is 3. I just looked right at Pascal's triangle. 2a to the first is going to be 2a. 5b squared is going to be 25b squared. And then finally, guys, for the last one, 3, 3 is 1. 2a to the 0 is 1. 5 to the third is 125. B to the third is b cubed. Okay? So all we did there, guys, was we just went through, we did the multiplication. None of it was too tedious, right? Okay. We're going to finish it off. We're just going to consolidate all those factors and simplify. So this is what I get. Okay, we'll check this in a second. 8a cubed plus 3 times 5 is going to be 15, and 15 times 4 is 60a squared b. And then 2 times 25 is 50, 50 times 3 is 150, so 150a b squared. And then finally the last one should be 125b cubed. Okay. While you guys are copying that down, let me use Wolfram alpha to show you that that is indeed the correct value, or the correct expansion for that. Okay, so I'm just going to go in here. I'm going to expand. What do we say? 2a, 5b to the third. So 2a, 5b to the third. Let's hope this is right. Otherwise, I have to go back and do the problem again. We don't want that. So we get 8a cubed, 60a squared b, 50ab squared, 125b cubed. So one of two things happened. Either A, I convinced you that this works every single time and we got lucky, or B, it actually works in the case. Okay? And in fact, it does work for every case.
Can you use Wolfram alpha in the exam?
You can, and in fact, what I'll do is I'll make the exam so difficult that you wouldn't be able to use Wolfram alpha for anything good. So I can do that, or we can just stick with this stuff. So I'll let you choose.
Take the exam by himself.
I can let him take the exam by himself. I think that's an excellent response, Mr. Weber. So, all right. So other questions, guys, I can answer about this. Okay, and you guys can clearly see the power of the binomial theorem. Okay, now. This probably would be like one of those problems, like I said, you could just probably cube it out in less time than it would take, okay? But if you start having 4th, 5th, 6th powers, then it might just be more reasonable for you to use the binomial theorem. So for the next example, let's just go ahead and expand out 3x minus 4y to the 4th power. Okay? And we'll see that it might be quicker than doing it, multiplying it out by hand. All right, first thing we have to do, we have to define a, b, and n. So we have 3x minus 4y to the 4th, and we want to expand that. Okay? So, what are a, b, and n for this example, guys?
A, b is 3x,
Good.
4y.
Negative 4y, good. Nice, okay? We can't forget about the sign, right, guys? If we forget about the sign, we're not going to get that alternating pattern that exists when we expand the binomial. Okay? So if I was to set up a series for this, now that I have a, b, and n, okay, here's our series. K equals 0. What's the upper bound of our series, guys? 4, right? That's the n. Okay? So we're going to have 5 terms, because 0, 1, 2, 3, 4. We would have 4 combination k, because it's n combination k. Okay? So again, all I'm doing is I'm just plugging into the binomial theorem. Okay? We're going to have 3x to the n minus k, or the 4 minus k, and then minus 4y to the k power. Okay, so does that make sense, guys, as to how we substitute back in? All I'm doing is I'm just taking the series from the binomial theorem, I'm substituting a, b, and n back into it. Okay, so it's not really as ugly as it looks. I know it looks horrific, but really, once you have this set up, all you do is you make k 0, 1, 2, 3, and 4, and you're done with it. Okay, so let's go ahead and expand this out. Okay, so by expansion, 4, 0, 3x to the 4 minus 0, negative 4y to the 0. Okay. So all I did there, guys, was I just made k equal to 0. I'm going to make k equal to 1. So we have 4, 1. 3x to the 4 minus 1. Negative 4y to the first. We have 4, 2. 3x to the 4 minus 2. Negative 4 to the, or negative 4y to the second power. 4, 3. 3x to the 4 minus 3. Negative 4y to the third. And then finally, 4, 4. 3x to the 4 minus 4, and then negative 4y to the... Okay, so let me get out of your guys' way, let you copy that down. Okay? But basically, all we're changing from term to term to term is we're just changing the bottom number. That's it. Okay, nothing else is changing. While you guys are doing that, I'll write up Pascal's triangle for the first 5 rows. So that way we can just use Pascal's triangle to evaluate the combinations. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Okay. By the way, this is independent of what we're doing. So I'll just put that off to the side. When you guys are doing your homework or taking an examination, might as well just do that. I mean, that took me, what, like 3 seconds to write up, rather than sitting there and punching it in the calculator each time. Okay, that gets very, very old very, very quickly, right, guys? This is much more convenient to evaluate small combinations. Okay, let's go ahead and do it. Okay, everybody good, guys? Any questions before we go on? Okay, good. 4, 0 is 1. Okay, that's just the first entry in the 5th row, okay, or the 4th row if you count the first row as 0. 3x to the 4th, that's going to be 81x to the 4th. Negative 4y to the 0 is 1. Okay, so it looks like our first term is just going to be 81x to the 4th. Okay. Second term, 4, 1. We could fumble and stick around with our calculator and eventually get 4, or we can just look at Pascal's triangle. It tells me 4. 3 to the 3rd is 27. And then we have an x cubed. And then we're going to have times a negative 4y. I want you to notice that I put it in parentheses for the negative 4y, just because I know at the end we're going to get a negative coefficient out of that. Okay, and I don't want you guys losing that negative value. Okay? For the next term, 4, 2 we know is 6. 3 squared is 9. X squared square is square. Negative 4 squared is 16. And then y squared. Okay. And then we're going to have 4, 3 is 4. 3 to the 1st and x to the 1st is 3x. Negative 4 cubed, y cubed is negative 64y y to the third. Okay. And then finally, for the last term, 1, 1. And then 4 to the fourth is going to be 625. No, 256. I was thinking of 5 to the fourth, sorry. So that's positive 256 y to the fourth. Okay. And by the way, this is exactly how a computer, when you guys type this into your TI-89, okay, this is exactly what the TI-89 does. And now you can get a real appreciation for how hard the TI-89 or Wolfram Alpha or any computer algebra system has to work. Okay? Yeah, I know. It's just on fire. All right, let's finish this off. Okay? So if we finish this animal off, I'll go over here to finish it. So we have 81x to the fourth. That's easy. And then we have 4 times 27 is 108. 108 times 4 is going to be 432 negative, maybe.
Yes.
And that's going to be x cubed y. Okay. And then over here,
864.
864.
I was getting there. Let me try it. Well, now I don't even want
We ruined it for you.
It's okay. I actually wanted to see if we could get it without using any calculator whatsoever, or anything like that.
Well, we paid for the calculator, so
What's that?
we paid money for the calculator.
Yeah,
so
but I wanted just to show you guys like the appreciation for like how hard it has to work to do that stuff.
We don't appreciate it.
Obviously not. Okay.
You want us
And
to
then
let you do the next one?
what's that?
You want us to let you do the next one?
I'd like to, but okay. So 4 times 64, that's going to be 256. 256, that's going to be 764.
8.
8. Okay. Sorry.
Now you see why we deal with it.
Yeah, that's true. I mean, I could have written it up and probably gotten it better instead of doing it in my head. And then the last one's just 256 y. Okay. Now, of course, we have no idea if this is actually going to be correct until we actually use a computer algebra system. Okay. So let's just go back to Wolfram Alpha, see if it'll do it for us. Okay. So that was going to be, what did we say, 3x minus 4y. And this time it was to the 4th power. The suspense is killing me. Not really. Okay.
That's it.
There we go. Okay. So if you guys check this out, 81x4 minus 432, 864x squared y squared. So, yep. Looks like it works out pretty nicely. Okay. So like I said, guys, this is exactly the algorithm that any computer algebra system would go through. Okay. And you guys can clearly see that this gets very complex just for the 4th power. Okay. Remember before I was typing in the 6th power? So we'd actually have to tack 2 more onto this and do the computation of that. So I think it's pretty neat how it does it. And hopefully for those of you guys that have ever used a computer algebra system or a TI-89, you get an appreciation of how some of those things work. Okay? I always try to teach how the computer works with that stuff. So, did you have your hand up, Dave? Yep, okay, fine. I don't want to talk to you either. All right. I wouldn't want to talk to me either at this point. Okay. Other questions, guys, I can answer?
So, like this one I was checking. So we have to expand it to 9.
Well, okay. So the next set of problems that we're looking at, okay. This one says just find the coefficient of the given term in each of the expanded binomials. So no, you don't have to expand it out 9 times. You just have to find the term that matches A6, B6 in that expanded binomial. That's all we're doing.
Okay.
Okay? So, Don?
How many of these are you going to give us in the class?
How many am I going to give you, or how many am I going to give everybody? Well, I don't know. I mean, these are just, I mean, when it comes down to it,
This is tedious, and if you make one mistake
oh,
anyway,
no, it's almost like you're in a math class. Wow. I will give you one of these, and I will make it no larger than the 4th power. Okay?
that's
Quite honestly, like, I mean, if I didn't have to
It's
sit
not bad, but
here.
it's just tedious.
Yeah, I understand that,
And
right.
if you do make a mistake in one spot, like, the whole thing becomes wrong.
Right, but that's why I always ask you to show all your work, so that way if you make a sign error, I give you 4 out of 5 points for it. Okay, yeah, I wouldn't kill you guys for like a sign error. Now, of course, if you just give me, like you go from here to that, okay? I guess it's worth like a point for punching it in the calculator. Yeah. If you can do that in your head, let me know. All right. Let me, first of all, before we actually do these problems, let me explain as to why these might be important, okay? A lot of times in mathematics, okay, we like to use polynomials to represent trigonometric exponential functions. So for those of you guys that have suffered through Calc 2 or even done like some interpolation with engineering, like for example, you guys might remember, don't write this down, but some of you guys may or may not remember that the sine of x is actually represented by the infinite series n equals 0 to infinity minus 1 to the n x to the 2n plus 1 divided by 2n plus 1 factorial.
That's a Taylor, right?
What's that?
Taylor
Yeah,
series.
that's a Maclaurin series, actually.
Maclaurin,
Okay?
right.
You can center it around something else. But that's an expanded polynomial. It's a power series. Okay?
How many years did you have to teach before you remembered that?
Well, actually, this one's easy to remember.
This is very easy.
Yeah, it's
Sine,
very-
cosine.
Yeah, because sine's an odd function. 2n plus 1 is the definition of odd. It's almost like that's why they call it an odd function. Oh, wow. Do you guys know that, by the way? Yeah, that's why they call them even and odd functions. For those of you guys that have suffered through any sort of series stuff.
Wait, what?
What? What? No,
What?
you asked me what? Oh, this is the definition of odd, right?
Yeah.
Sine's an odd function because it's symmetric about the origin. That's why it's called an odd function, because it has 2n plus 1 in it. Yeah! Damn! Cosine. N equals 0 to infinity minus 1 to the n, x to the 2n divided by 2n fact. Cosine is an even function. No, for real. I'm being deadly serious. That's why they're called even and odd functions.
You
So
can't say for Rizzle and
I
be
can't.
serious.
I'm absolutely serious. But yeah, I'm surprised. Like, none of your teachers in pre-calc or college algebra said like that's why it's an even and odd function. They said, oh, it's just an even function.
They just drew the
Wow. So they're just telling you information and it's like you just believe it. Okay, that's why it is. Okay, so yeah, if anybody's ever on Jeopardy or they want to know why it's called an even or odd function, that's why it is. But anyway, back to the point of what I was trying to make as to why these, like why would I ask you guys to do this problem? These approximate trigonometric functions. This is a polynomial. Like for example, this would be equal to x plus x cubed over 6 plus x to the 5th over 120 forever, okay? That's a polynomial, right guys? Polynomials are much, much easier to work with. In fact, in your calculator defines sine of x by this function. Calculator doesn't know sine x. Mathematica doesn't know sine x. Wolfram Alpha doesn't know sine x. It knows this series, okay? So when you guys are doing that in your calculator, you're really just using that series. Now, your calculator does is it goes out to maybe like 40 places. In other words, 40 terms in the polynomial, okay? So what you're really getting is you're getting an approximation in your calculator. A really, really, really good approximation, okay? But it's still an approximation. But sometimes in mathematics, we like to use approximations, and one of the coefficients has a large residual, okay? Does anybody know what a residual is, by the way? I threw that term out there just
Leftover.
Well, like more than leftover.
I mean like the error, like original number minus the whatever the thing
Estimated,
is.
right.
Yeah.
The
so
estimated versus the actual. Like for example, you guys have all seen like a line of best fit, right guys? Like where you have like some points and you draw the line through it. So like this would be the line of best fit. This is a residual, okay? The distance between the line and the point, okay? So sometimes what happens in mathematics is we like to find the coefficient that has the largest residual because then we can figure out where the function actually has meaning and not meaning, okay? So that's why I'm asking you guys to look at this exercise is because sometimes we want to try to figure out where does it actually model the function correctly, where does it not model the function correctly. And how many of you guys remember, like in Calc 2, well, probably not, but that's okay. Sometimes you can figure out like the error in figuring out like a Taylor or Maclaurin series at a specific point. That's exactly what part of this is. It's like finding the coefficient that has the most or least error. Okay? By the way, polynomial fitting is extremely important in mathematics. Okay? I could make a whole class out of polynomial fitting if I wanted to, but anyway, like I mean like an entire like 15-week semester out of it, not just like one class. I actually used to teach an engineering course where we did stuff like that, mathematical, like numerical analysis of stuff.
Is that the one I took?
Yeah, it is. It's the one you suffered with through me. So, but yeah, what we did in that class was we did polynomial interpolation. We used MATLAB to be able to build programs and that sort of stuff. We found like numerical approximations to differential equations and all kinds of stuff that you would use in real life. But then they figured out that course, I guess, would never be useful to anybody because, you know, yeah, it would probably be the most useful course in most people's career. But regardless, they decided to get rid of it just because it doesn't transfer. So anyway, yeah, makes sense. Anyway, all right. So we want to just figure this out, right? That's where we're at. So sorry about that. Didn't mean to go off on a tangent, which is an odd function.
It's 3-1, not 5.
Is it 3-1? Okay, sorry about that. I don't know how that 5 out.
We can do 5 lines.
Yeah, we could do it, but I don't want to confuse
It
anybody.
ain't what we asking for.
Yeah, that's just asking for 7 emails. All right. So guys, all we're trying to do is we're trying to figure out what the coefficient is of this expanded binomial. Okay. By the way, we can check this answer in Wolfram. Okay, we're going to do so. Let's go ahead and identify, first of all, what A is, what B is, what N is, and then what K is. Because if we get those 4 things, then we can just immediately go right to the answer. Okay? A, B, and N should be obvious. Guys, what are A, B, and N respectively in this problem?
2x, 3y, 7.
Is that okay with everybody, guys? You can't get those wrong. Well, you could, but you'd be pretty embarrassed if you did. Okay? A, what's that?
Oh, I'm just jumping in.
No, that's okay. Go ahead.
K is 5.
Yeah, K is 5. Okay, there's a multitude of ways to get K. Guys, isn't K the exponent affixed to the second factor in the expanded binomial? So one way that you could get K is you could just look at the expanded binomial and you could say, oh, okay, well, it's a y to the 5th, so that would be K. Isn't it true, guys, that 7 minus 5 is equal to 2? Or in other words, n minus k is equal to 2 in this case. So we could just easily substitute for n and solve the linear equation that way. It's probably just easier to look at the last one and see that it's 5.
Or the greater one? Should we look at say the greater one?
Not the greater one. No, no, no,
Always
no.
the second.
It's the second factor's coefficient.
Oh, second factor.
Okay? All right. Does that make sense to everybody, guys? Now what we're going to do is we're just going to plug it into the formula. Okay? So remember the formula that we have. We have n combination k, a to the n minus k, b to the k. We already know what n, k, a, and b are going to be, so let's just plug in. Okay? So we get 7 combination 5, 2x to the quantity 7 minus 5, and then b, which we said was 3y to the second power. Okay, so all we did there, guys, we just used one term of the binomial series because we are looking for the coefficient of that term in the binomial series. Okay, does that make sense, guys? How we define a, b, and k?
3y to the 5th. Second, because it's...
Yeah. I'm sorry. I put in the n minus k. Okay, gotcha. Is that what you were going to ask, John? Okay, sorry about that, guys. Okay. So I just substituted k incorrectly there. Okay, is that better, guys? Any questions about that? Sorry about that, boo-boo. Okay, now all we're going to do is we're just going to evaluate, and then we can be done with this, okay? 7 combination 5, we could write out Pascal's triangle if we wanted to, or we could just get 21 out of it, okay, whichever one you guys prefer. In fact, we proved that one earlier. Okay. 2x squared is going to be quantity 4x squared for that. And then 3 to the 5th is going to be 243. And then we have y to the 5th. Then we're just going to multiply it out. Okay, this is what I'll ask for you guys to use your calculator on just because it's a little bit inconvenient. So, was anyone able to figure out what the product is of the coefficient?
20,412.
20412. Does that sound good, guys? Okay. Now we have the x squared y to the 5th. But really all we care about is the coefficient, okay? Because the question says, find the coefficient of the missing binomial, okay? So that's all we're going to do with that, okay? Let me just verify to you guys that that does work, okay? I'm going to expand the binomial. using Wolfram alpha, so we have 2x to 3y, this time it is 7.
Do you have to be a member to use that?
No, sir. You can just go through and just use it if you want to log in. Yeah, that one's completely free. It doesn't have all the nice stuff that Mathematica does, but it has like a lot of stuff. I don't think there's anything in here that you guys would ever use it for more than what's in there. So yeah, it's a really nice tool.
Yeah, the only thing about the pro version, I think, is it gives you actually all the steps.
Yeah.
And
But
it's
you
not
got-
how it gets its answer. So it'll give you really complex solutions, but it won't give you all the guides, like step by step how to do it.
By the way, guys, if you look at the term of x squared y to the 5th, 20412, 20412 is right there. So it does work. Okay. All right. So we'll stop here. Next time, what I'll do is I'll do the other 2 of those, and then we'll also take a look at how do we go backwards from the series to the binomial. Okay. I do have some. Oh, go ahead, Jen.
Assignment 10 is due.
Assignment 9 is due next class. And assignment 10 is due the following Monday, which I believe, correct me if I'm wrong, is that the 14th, guys, for November?
Yeah.
Right, no, not at Thanksgiving.
I said after the test.
Right. So assignment 9 is due on, what did we say, November 7th, is that correct, guys? Okay, and then assignment 10 is going to be due on Okay, guys, so let me go ahead and give you guys back your assignments from last time, okay? Make sure you guys check the solutions, in particular to the, to some of the problems involving the axiomatic definitions.